what we call thermal dark matter is the idea is that you start with your dark matter particle in thermodynamic equilibrium with everything else. And then the universe cools, the dark matter falls out of equilibrium, and you're left with some remaining density. So that's the thermal story. The non-thermal story is that the dark matter, the dark matter didn't really start off in thermodynamic equilibrium. It was produced in some other way. It didn't start from a thermodynamic equilibrium situation. So one example is, for example, the production of gravitino dark matter from standard model superpartner decays. So there you can start with your standard model superpartners in thermodynamic equilibrium, but not the gravitino. The light of standard model superpartner freezes out, and then it decays at some later time to the gravitino. And that gravitino density is not set by the gravitino thermal abundance. It's set by some other mechanism. So this is called non-thermal. And I'm going to give you a couple of other examples today, and then switch gears. So one thing I do want to mention about gravitinos before I move on is that there's also a second case that I didn't consider. And this is the case when the gravitinos aren't the dark matter, but they can also contribute to the dark matter density. And in this case, when the gravitino mass is larger than some of the standard model superpartner masses, the gravitino in this case is going to decay to some of the standard model superpartners. So the decay rate in this case for the gravitino to decay to some superpartner and standard model particle. So this is a standard model particle. This is a superpartner. Up to some constants, it's basically just m3 halves squared, sorry, m3 halves cubed over m Planck squared. And I can convert this into a lifetime. So the lifetime is just 1 over the decay width. And numerically, if I plug in numbers, I find that this lifetime is roughly 1 second divided by 10 TeV over m3 halves to the cube power. So this actually becomes interesting because suppose there's some initial abundance of gravitinos. This initial abundance of gravitinos will do two things. The first is that the initial abundance of gravitinos will contribute to the dark matter. In this case, the dark matter particle is a standard model superpartner. And depending on the initial gravitino abundance, I'll get some contribution to the dark matter, to the regular dark matter, the superpartner dark matter from the decay. But the other thing I have to worry about is that when this decay happens, I'm going to get some particles here from the decay. I'm going to get some superpartners, which go into dark matter. But I'm also going to get some standard model particles. And these standard model particles have a lot of energy. And because they have a lot of energy, they're going to enter the cosmological plasma and bang around, and they might do bad things. So one of the bad things that can happen if the decay happens after about 1 second is the decay products can destroy the light elements made in nucleosynthesis. So nucleosynthesis is a process where free protons and neutrons glomp together into light elements. And this process of glomping together in nucleosynthesis starts when the universe has an age of about 1 second. So if my gravitino starts to decay after 1 second, so for gravitino lifetimes larger than 1 second, this means that the decay products are going to enter the cosmological plasma after nucleosynthesis has started, and they're going to start destroying some of those light elements. And if you destroy too many light elements, the predictions of nucleosynthesis wouldn't agree with observations. So people have done careful studies of this kind of decay. And what they find is a limit on the reheating temperature. In this case, remember the reheating temperature is going to set the gravitino abundance. The larger the reheating temperature, the more gravitinos I produce. And people write these limits as a function of 10 to the 2, 10 to the 3, 10 to the 4. For a given gravitino mass, you can put limits on this kind of decay, given a certain reheating temperature in GeV. And so the point is the larger the reheating temperature, the larger the initial gravitino abundance. And also, the smaller the gravitino mass, the later the decay happens, and typically the more damage you do to nucleosynthesis. So you can actually, I have a nice diagram in my notes, but start to sort of 10 to the 6 GeV. It goes up all the way to about 10 to the 10 GeV. And the point is you get different regions ruled out by different light element abundances. So for example, this region is ruled out because you start destroying the abundance of helium-3. So everything up here is ruled out. This region is ruled out because you start destroying deuterium. And then there's some other lines where you start destroying regular helium. And then up here, there's also a limit from the fact that for a very large reheating temperature, I produce too much dark matter. Because remember, these decays are also going to produce superpartners, which will cascade down to the lightest, superpartner, and that will make dark matter. And the point is that the larger the gravitino mass, the earlier the decay happens. And if the decay happens before about 1 second, you don't care anymore. It's not a problem anymore that if it has before 1 second, you don't destroy any light elements because they haven't been created yet, so you're safe. But you still have to worry about producing too much dark matter. So I just wanted to mention this in passing. So this isn't so much a dark matter story as it is a gravitino story, but gravitinos come up a lot, and it's handy to understand how they work. Okay. So gravitinos give you one example of non-thermal dark matter, and they can be produced in various different ways that are non-thermal. If they're produced thermally, then things are bad, so you don't want that to happen. I want to move on next to a slightly different scenario of non-thermal dark matter production, and that is from massive particle decays. So this is another way to get dark matter. And the idea here is that I have some heavy particle that I call P. And the lifetime of this P particle, which is 1 over its decay width, is very long. So it's a heavy particle with mass mp, and it decays, but it decays very slowly. And what can happen in this case is that if I start off with an initial abundance of P particles, the abundance of P particles, as the temperature falls below their mass, I have some initial density. If this density is big enough, as the universe redshifts, the energy density in P particles will redshift more slowly than the energy density in radiation. And the P particles can come to dominate the energy density of the universe. But they're only going to dominate the energy density of the universe until they start decaying away. So the very rough picture is that if I plot the various energy densities versus time, I start off with radiation, but I also have some P density, and the P density redshifts more slowly. So this is my P density. And if I wait long enough, the P density can come and dominate the energy density of the universe. But it can only dominate until it decays. So at some point corresponding to the lifetime, the energy density in P particles decays, and the energy density in radiation jumps up. And I transition from a phase where I'm matter dominated by P here to a different phase where now I'm radiation dominated again. And I've gone from what's effectively a very low temperature to a much higher temperature because of the P decay. And this process is called reheating. So this picture is actually a bit schematic. What actually happens, let me redraw this. What actually happens is that what actually happens is the radiation density falls, and then because of the decay start happened, it actually decreases more slowly, and then it takes over kind of over here. So this isn't quite exactly accurate, but I'll calculate this stuff in a second, or at least estimate it. So what can happen in this case when I go from radiation domination to P domination? When P decays, some of the P decays can produce dark matter. And the point is that if this reheating temperature of the radiation after the decay is less than the freeze-out temperature, the dark matter you produce in these decays will be left over. It won't be able to reannihilate. So let me put this into a set of evolution equations that describe what happens. So I can describe the situation quantitatively by writing evolution equations for the energy density in P particles. And we assume that this energy density is acts like matter. So I have a 3 here. But I also lose energy density to P particles at the rate given by the decay rate. So this is the first thing. The second thing is that if I write the radiation density still redshifts with the usual 4. But now, because the P decays produce radiation, they're going to produce radiation with some fraction 1 minus epsilon. So this 1 minus epsilon here means that not all the P decays go to radiation. A fraction epsilon is going to go to dark matter. So what I mean by that is that we also have an evolution equation for the dark matter density, assuming the relative temperatures are below the dark matter mass, of epsilon, gamma p, rho p, over mp, minus the usual sigma v n chi squared minus n chi equilibrium squared. So I have these equations, and then I also have my Hubble equation, which is h squared is equal to a dot over a squared is equal to 1 over 3 m Planck squared rho r plus rho p plus rho chi. So these are my evolution equations for this system. And the structure of them is fairly straightforward. The part on the left-hand side just describes the dilution of the P density with the expansion of the universe. But I also lose the density in the P particles from the fact that the P particles decay. And the rate at which the P particles decay is proportional to their number density. And because I'm assuming that P's are non-relativistic, this is just MP times the number density in P. So this decay term is going to remove P density from decays. The radiation term is similar. Here, the radiation redshifts like radiation usually does. I have a 4 here. But I also produce radiation from P decays. So this source term tells me that the P decays produce radiation at this rate. And finally, if some fraction epsilon of the P decays goes to dark matter, I have a factor of epsilon here. I have my number density in dark matter here. And some fraction of the P's go to dark matter, so this sources the dark matter particles. But this term over here tells me that I can also have dark matter equilibration from annihilation. So the non-thermal case of interest is when so the non-thermal case of interest is when T decays, I end up reheating the temperature to some effective temperature T reheat. And if T reheat is much, much less than T freeze out, this implies that the sigma v term is negligible. And if you take these equations, and if I work in this limit, I can ignore this term. If I take these equations and solve for them, what I find is a yield for dark matter Okay, so first of all, it turns out you can compute the reheating temperature, and you'll do this in the tutorial. The reheating temperature is approximately G star to the minus 1/4 m Planck times the P decay width to the 1/2. And you can show that in the limit where I can ignore this term, the yield of chi's from these P decays, y chi, is roughly epsilon times the reheating temperature divided by the P mass. So you'll go over this case a little bit in the tutorial tomorrow. It turns out that it's actually, instead of solving these equations, it's a pretty good approximation to just treat the decay of the P particles being instantaneous. And in this case, in this case, when the decay happens, you have h going like 1/t. And if the decay is instantaneous, that means that whatever energy density you had in the P decays gets transferred over to radiation. And if you solve for the temperature of the radiation by matching the energies, you get out this result. And it's also straightforward to do the same for the chi density and get this result. But let me emphasize again that this result only applies when I can ignore this term. On the other hand, if in the case when the reheating temperature, let's say, is larger than the freeze-out temperature, what ends up happening is that I might produce some chi particles. But if the temperature is a lot larger than the reheating temperature, these chi particles can equilibrate. And in this case, the density is just set by the thermal abundance. So for this to be really non-thermal, you need typically a reheating temperature that's less than the freeze-out abundance. And I guess tomorrow in the tutorial, you'll go through and essentially derive these in the limit of treating the decay as being instantaneous. Okay, and then I have some plots in my notes that show essentially the interpolation between this totally non-thermal case and the case where the reheating temperature is larger than the freeze-out temperature, and the dark matter just re-equilibrates after being produced. Okay, so I want to mention one last non-thermal mechanism. And the last non-thermal mechanism, but this has been fairly popular recently, is something called asymmetric dark matter. And asymmetric dark matter works a little bit differently from what we've done so far. So for asymmetric dark matter, let's forget about dark matter for a second and think about how you get a baryon density. So in the case of baryons, what ends up happening is that your plasma has lots of quarks and gluons and antiquarks. And fairly early on, the quarks and antiquarks bind into baryons and antibaryons. So I can have, let's say, a baryon B and an antibaryon B. But we know that baryons and antibaryons, and by baryon I just mean typically a proton or a neutron, or antiproton, antineutron, we know that baryons and antibaryons can annihilate into a pair of photons. And they annihilate fairly efficiently into photons. So what happens for baryons is, because this annihilation is very efficient, if I started with equal numbers of baryons and antibaryons, it turns out that the annihilation would be so efficient that I would expect a net baryon density today to be roughly 10 to the minus 12 if we had equal numbers So if we had equal numbers of baryons and antibaryons, we would find today just a really, really tiny baryon density. Yes?
That's for the same reason that we expect some amount of dark matter to be in the dark matter, anti-dark matter.
Yes, yeah. Okay. So in this case, we have distinct baryon and antibaryon particles. But they annihilate very efficiently into photons. And this process will eventually freeze out. But it's so efficient that the relic density you would expect is tiny. It's sort of 10 to the minus 12, whereas the observed value is something like 0.0 I think it's something like 0.03 or so. So 0.03 is not huge, but it's much, much bigger than 10 to the minus 12. So the actual story for baryons is not so much that, well, the actual story for baryons is that we know that we have more baryons than antibaryons. So the thing that actually sets a baryon density isn't this freeze-out process. It's the asymmetry between baryons and antibaryons. So the point is that annihilation of these baryons always involves one baryon and one antibaryon. You can't have two baryons annihilate into something with no baryon number because baryon number is conserved. So for example, I can't annihilate two protons, but I can annihilate a proton with antiproton. So the story for baryons is that through some unknown process that we call baryogenesis, and there's a lot of speculation and research on what kind of mechanism baryogenesis actually is, but through a mechanism that we call baryogenesis, there must have been created more of a density of baryons than antibaryons. So baryogenesis just means that some process that creates more B than anti-B. And what happens in this case with baryogenesis, if I have more baryons than antibaryons, the baryons in the plasma, well, all the antibaryons in the plasma will annihilate with the baryons. But once I run out of antibaryons, I can't have any more annihilations. So just to draw a dumb picture, suppose I start with a universe with 3 baryons and 2 antibaryons. I lost my chalk. This is fairly self-evident, but if annihilation is very efficient, I'll annihilate baryon with antibaryon, baryon with antibaryon, but I'm going to be left over with an extra B. So the idea of baryogenesis is some unspecified mechanism creates more baryons than antibaryons. And the fact that baryons can only annihilate with antibaryons means that once I run out of antibaryons, what I'm left over with, I'm stuck with. So the point is that if I produce enough of an excess of baryons over antibaryons, I can get this relic density. And it turns out that the actual excess of baryons over antibaryons that I need early on in the universe is something like 1 part in 10 to the 10. So it's actually a very small asymmetry between the two. But that small asymmetry between the two is still enough to give me this final relic density. So the idea of asymmetric dark matter is to essentially take this picture and just copy it for dark matter. So for asymmetric dark matter, or ADM, I have distinct chi and chi bar that are distinct. And I have some conserved charge where this chi carries the conserved charge, and the anti-chi carries the opposite value of the charge. And if this charge is conserved, that means that chi can only annihilate with chi bar. This is the story for baryons. The corresponding charge here is baryon number charge. So for asymmetric dark matter, only chi bar annihilation can happen. And through some dark matter genesis mechanism, you create more chi than chi bar. And there are various limits. But if the annihilation of chi with chi bar if the annihilation is very efficient, only the asymmetry remains. So there are various theories of how this asymmetry could be created. That's kind of the tricky part. But one kind of interesting tie-in of asymmetric dark matter is this mechanism works just like baryons. And one thing we also know observationally is that the observed density of baryons is actually very similar to the observed density of dark matter. In terms of omega h squared values, they differ by about a factor of 5. And this also seems like a bit of a puzzle because we have typically one mechanism for creating dark matter and some completely different baryogenesis mechanism for creating baryons. And in principle, the two densities could be orders and orders of magnitude different, but they happen to be equal to within a factor of 5. So this could just be an accident, but maybe there's also some unified origin for both dark matter and baryons. And one of the variations of asymmetric dark matter is that perhaps whatever creates more baryons and antibaryons also creates more dark matter than anti-dark matter. So in this case, if the dark matter genesis is related to baryogenesis, what you would expect typically is the number density of dark matter to be similar to the number density of baryons. And that means that to get the relative factor of 5 in the energy fractions today, you would expect roughly your dark matter mass should be roughly equal to the baryon mass, which is about a proton mass, times the ratio of the energy densities today. And this is roughly 5 GeV. So a very rough prediction for asymmetric dark matter, assuming that the dark matter creation is related to the baryon creation, is that the dark matter mass, you would typically expect it to be not too different from the proton mass. So there are various searches for dark matter motivated by this tie-in. Yes?
Could dark matter be not a fundamental particle like the way the protons?
Sure, that's possible as well. Now, whether the fact that it's non-fundamental matters a whole lot or not depends on the energy scale at which it becomes a bound state versus the energy scale at which all this dynamics happens. So in the case of baryons, the actual bound state dynamics happens before the baryon-antibaryon annihilation takes over. Okay. So this is another example of asymmetric dark matter, and there are lots of other examples, but just in passing, as a take-home story, I want you to remember that even though kind of the standard story for dark matter creation is this thermal freeze-out, there are lots of other ways to make dark matter. And these other ways to make dark matter can have interesting implications. So for example, suppose I produce my dark matter through this non-thermal mechanism, through P decays. In this case, it could turn out that the annihilation rate I would expect for my dark matter could be much larger than the annihilation rate that would give the right thermal freeze-out relic density. So in this case, I could have a very large annihilation cross-section, but still get the right dark matter density. And this could have implications today. So for example, if the dark matter has a very large annihilation cross-section, we might be able to see its annihilations in our galaxy today. So this kind of scenario could give you an enhanced signal from the so-called indirect detection, where dark matter annihilates in our galaxy and we see the cosmic rays produced. On the other hand, for asymmetric dark matter, if dark matter can only annihilate with anti-dark matter, and all the anti-dark matter is annihilated away, in this case, there's no annihilation today, because we've used up all the anti-dark matter, and in this case, you'd expect no cosmic ray signals from dark matter. So these different kinds of production mechanisms actually tie into different dark matter signals today. Okay, so that's the end of what I'm going to talk about for dark matter creation for the time being. I'm going to come back towards the end of the course and talk about another non-thermal kind of dark matter that's produced in a totally different way. And this other kind of dark matter is something called axions. They tend to be quite different, so I'm going to leave it to the end. But the thing I'm going to move on to next is something called dark matter direct detection. And direct detection of dark matter means that we try to find the dark matter that's bouncing around this room in some kind of very sensitive experimental apparatus. So again, we have all this evidence for dark matter from its gravitational influence. What we really want to probe are its particle physics properties. And for that, we need to do various kinds of experiments. So as far as probing the dark matter very close to us, experiments are these things called direct detection. And remember, for direct detection, the picture is that we have dark matter floating around the room. And this dark matter can come in, and it can exchange, it can interact somehow with, let's say, a quark. And the quark could be part of a proton. So my dark matter comes in, it interacts with a quark somehow, and dark matter scatters off. And because the dark matter is basically invisible, I don't see this, I don't see this. But what I do see is that my proton and my target, or my neutron and my target, can recoil for no good reason. So the way these experiments are set up, I take a big detector, I put it deep underground, I wait for a dark matter particle to come in, to hit something in my detector and bounce off. But when it hits something and bounces off, my nucleus, which started off essentially at rest in my detector, is going to recoil. And I look for nuclear recoils with no other explanation. So the signal of dark matter direct detection is nuclei in my sample, in my detector, recoiling for no good reason. And these experiments give us some of our best limits on dark matter. And there's a whole set of technology to actually computing both the particle physics and the astrophysics to get the rates of this kind of interaction. So that falls under dark matter direct detection. So for this, we need, to compute dark matter direct detection, we need a couple of pieces of information. The first thing we need to know is we need an estimate of how much dark matter we have around us and how quickly it's moving. So our estimate for the local dark matter energy density is roughly 0.4 GeV per cubic centimeter. So 0.4 GeV per cubic centimeter, if I have a 100 GeV dark matter particle, this corresponds to roughly 1 dark matter particle per teacup for 100 GeV dark matter particle. So we expect that, that for reasonable dark matter, or for dark matter masses, let's say in the WIMP range, there should be lots of dark matter particles floating around this room. So they're going right through us, they're zipping through the room, who knows what. So the first thing we need to know is this density, and we're pretty confident in that. The second thing we need to know is what the local dark matter velocity distribution is. Because the faster the dark matter is going, the larger the recoil energy of the target nucleus will be. So the second thing we need is the dark matter energy, the dark matter velocity distribution. And for that, let me draw a cartoon of our galaxy. So the cartoon of our galaxy is a flat disk. And we're sitting out kind of over here. So this is us. And then we're a distance of roughly 9 kiloparsecs from the center of the galaxy. And we're rotating around the center of the galaxy. And on top of this, we're surrounded by a big halo of dark matter. And this dark matter halo, on the average, has no net velocity, or we expect it not to have a net velocity. So first of all, we see a net dark matter wind from the fact that we have this halo of dark matter surrounding us, and we're rotating around within it. So that will give us automatically one contribution to velocities. But it also turns out that the dark matter within the halo, even though it has no net velocity on the average, it has a velocity distribution. So just like the air in this room has no net overall velocity, there's some distribution of air molecule velocities bouncing around the room. So to describe these two effects, first of all, the wind that we see from moving through the dark matter halo, and secondly, the distribution of dark matter velocities from the fact that they bounce around, we describe this with a velocity distribution. So the velocity distribution is a function f of v. I think I told you about this before. And the way we write the velocity distribution f of v, a standard assumption, and this seems to be confirmed by simulations of dark matter in our galaxy, is that this velocity distribution is approximately a Gaussian. So this is the dark matter velocity distribution. But this is the dark matter velocity distribution in the halo frame. So what I mean by this is if we were at rest relative to the halo, if we weren't rotating around, this is the dark matter velocity distribution we'd see. It'd just be this Maxwellian form. And it turns out this V escape is roughly 220. Sorry, this V0 that sets the size of the Gaussian is roughly 220 kilometers per second. That corresponds roughly to the average dark matter velocity. And this V escape is roughly 600 kilometers per second. So if the velocity of the dark matter is larger than V escape, you have enough velocity to actually escape from the galaxy. So we only expect dark matter particles with velocities less than the escape velocity to be bound within the halo. So this is our distribution. This n is approximately equal to 1. But specifically, it's chosen such that d3v, f of v, is normalized to unity. So this is just a distribution. It's normalized to unity. And it would be normalized to unity if we didn't have this step function. This turns out to be the correct normalization for this, integrated over d3v. But because we cut off essentially the velocity radius, we have to correct for this correct for this cutoff by modifying the normalization. But since the escape velocity is much larger than the thing that goes here in the denominator of the Gaussian, this is only a very small chop far out on the tail of the Gaussian, so the effect on the normalization is very small. So if you like, you can set the normalization factor equal to 1, but it's very slightly different, very slightly less than 1, sorry, very slightly larger than 1 to account for this cutoff. Okay, so this is the velocity distribution of dark matter in the halo, and we need to transform this velocity distribution in the halo to our lab frame. So in our lab frame, we're moving around with the sun. But we're also moving around relative to the sun, because if this is our sun, the sun's rotating along with the galactic disk, but we're rotating relative to the sun with an additional velocity. So in other words, here's the sun, and obviously we're being on the Earth, we're rotating around relative to the sun. So depending on where we are in our orbit, our total velocity relative to the halo frame can be a bit different. So to handle this, it turns out that the typical velocity of the Earth has two components. It has one component from the rotation. So the component with respect to the rotation turns out to be roughly 230 kilometers per second. So this is from the galactic rotation. But on top of that, we have an extra rotation around the sun. And this will change our relative velocity a little bit. And the extra velocity of rotation around the sun gives us a factor of roughly 15 kilometers per second times a sine function, where the frequency of this corresponds to 1 year, because that's how long it takes us to go around the sun. Okay. So this is our actual Earth velocity relative to the halo. And we need to convert our halo frame dark matter distribution into a distribution of velocities in our lab frame. And this part is this is a straightforward thing to do, and it's just a matter of it's just a matter of shifting the velocity to the Earth velocity. So, given that we've done that, given that we transform from the halo frame to the lab frame, given that we transform to the halo frame to the lab frame, we have our lab frame velocity, v prime, just equal to the velocity of the Earth plus the velocity in the halo. We can write down the scattering rate for dark matter. We can write down the rate for dark matter to scatter of targets in our detector. And the way we usually write the dark matter scattering rate is as a differential rate per unit energy. So we write the rate per unit energy. And this rate per unit energy is fairly straightforward to understand. We normalize the rate to the target density. So specifically, it's the rate per unit target mass. So this is the target density. So by multiplying by the target density, we normalize to the rate per target mass. And the rest of the rate is just going to be the dark matter flux impinging on us multiplied by the scattering cross-section, or in this case, the differential scattering cross-section. So for the dark matter flux, we need the local dark matter number density, which is just the local dark matter energy density, which we know to be roughly 0.4 GeV per cubic centimeter, divided by the mass. This gives us our local number density. And then we have to convolve this with the lab frame relative velocity. It's d3v prime. We have a factor of v prime because of the flux. We have the distribution function of dark matter velocities in the lab. And then we have the scattering cross-section of our target nucleus per unit energy. So this, if you like, is a scattering probability. This thing is essentially an average dark matter flux. And this is the target density. So this formula is very straightforward in its origin. I'm just taking the dark matter flux with a convolution of velocities, and I'm connecting that with the dark matter differential cross-section. And that gives me my differential rate per unit energy per unit target mass. Okay, and again, this f of lab just turns out to be the same distribution function I had before, this f halo, but now a function of v, which is v prime minus v Earth. So it's just a matter of here, this velocity is the Earth frame lab velocity, and I have to convert the halo frame to the Earth frame, so I just make that substitution. Okay, so this is the scattering rate. This is what I have. I have my velocity distribution. I have my local density. I have my scattering rate. So the only thing left, really, to compute is this differential cross-section, and then just do the velocity integration. So that's straightforward, but there are some issues in connecting a theory of dark matter into a scattering cross-section with nuclei. And there'll be a few different steps that we'll go through. First of all, we have to convert a dark matter scattering interaction with quarks and gluons into a scattering interaction with nucleons. And then we take that nucleonic interaction and turn it into an interaction with the target nucleus. Because in practice, our targets turn out to be fairly large nuclei. So there are lots of aspects of elementary particle physics, hadronic physics, and nuclear physics that all get lumped into one in here. So it's kind of an interesting mix. And I'll get to it in a little bit. But the first thing I wanted to do before any of that is just think about the kinematics of the scattering process. Because the kinematics of the scattering process influence are going to influence how we deal with this. So let me. Oh, that wasn't supposed to happen. Okay, so the kinematics of this are very straightforward, but it's useful to go through them. So the picture is that we have our dark matter particle chi impinging on a target nucleus. I'll call that n. And the dark matter comes in with some initial velocity v. And a typical initial velocity, given our distributions, will be on the order of 10 to the minus 3 units of the speed of light. So the dark matter is moving pretty quickly, but it's still very non-relativistic. So our dark matter comes in with some velocity v. It hits the nucleus. And then, so this is the before. The after picture is that the dark matter goes off with some momentum p prime, and the nucleus goes off with some momentum q and relative angle theta compared to the initial dark matter direction. So because we expect our v's to be very non-relativistic, we can expand our energy momenta non-relativistically. So for example, if my initial dark matter for density, if my initial dark matter 4 vector is that, corresponding to a dark matter particle coming in with momentum p, we know that p non-relativistically is just mv. Actually, I guess the full result is gamma mv, where gamma is usual 1 over 1 minus v squared. But remember, our v is like 10 to the minus 3, so gamma is basically 1. So that means that our p is basically just mv. And we also have that our energy is just m squared plus p squared, which, if I expand it out, just gives me m plus p squared over 2m plus higher order stuff. But I don't care about the higher order stuff because p is already very small compared to m, because, again, my v is very small. So we can just do a non-relativistic treatment of this scattering. And when you do that and you solve, you pose energy momentum conservation, you solve for the q, the momentum of the recoiling nucleus. This is the thing you actually measure. What you find is that q is just equal to 2 times mu n v cosine theta, where mu n is the nucleus dark matter reduced mass. It's mn m chi over mn plus m chi. And this angle, theta, lies between 0 and pi by 2, because my nucleus can't recoil backwards if the dark matter is coming in forwards. So this q corresponds to the amount of momentum transferred to the nucleus. And this is the thing we're going to go look for in our detector. And if suppose I plug in a nuclear mass of about 100 GeV, so a nucleus with about 100 protons and neutrons, and I take a dark matter mass of about 100 GeV, and I plug that all in here, this corresponds to a momentum transfer of about 100 MeV, so relatively small. I can also convert this into a recoil energy. So the recoil energy, this is the recoil energy of the nucleus. So it has momentum q and a recoil energy ER. ER, of course, is just q squared over 2mn. And getting out the q squared over 2mn, if I plug in this estimate, this turns out to be about 100 keV. Again, for a nuclear mass of about 100 GeV. So what I need to look for in my detector are recoils of nuclei within the detector with energies on the order of 100 keV. And it turns out that this is not so easy to do, but it's possible. And this is what experimental detectors have been designed and built to do. And the idea of these experimental detectors is you basically take a large sample of target nuclei, you shield them from any background radiation by putting them deep underground and lining stuff. And you set up your detectors such that your detector is sensitive to recoiling nuclei with energies of about that size. So this can be done. So there's actually a whole industry of experiments trying to look for dark matter this way. So let me see if I can get this to... So the step for us as particle physicists is to figure out how to compute the scattering cross sections. So the point is, suppose one of us has come up with a brilliant theory of dark matter, and this brilliant theory of dark matter produces the right relic abundance, we want to make predictions for that theory of dark matter in this kind of experiments. And the thing we have to do for our theory of dark matter for these experiments is effectively compute the d sigma n DER. So our job as particle physicists is to compute these differential scattering cross-sections. So what are these? OK, so I'm going to give you a few examples of dark matter interactions, and for these examples, show you how you compute these scattering cross-sections. Now, if we go back and we look at the typical energy in these events, and we look at the typical momentum transfer in these events, the numbers are pretty small. So for example, suppose we had a WIMP particle. A WIMP particle would only be able to interact with a standard model through weak interactions. So in other words, by exchanging either W bosons, Z bosons, or Higgs bosons. And the masses of all of those things are about 100 GeV. So that means that when if we were to exchange, for example, let's say I have dark matter particle come in, and I exchange a Higgs, and I interact with a quark this way. When I computed this amplitude, what I would find is that I would have a propagator factor for the Higgs that goes like 1 over I'll call it 1 over k squared minus m Higgs squared. But this k, this k corresponds to the momentum transfer, and the k roughly has components ER and Q. And when I take the square of this k, what I find is something that's really, really small compared to the Higgs mass. So what I can do for this interaction is instead of treating the interaction as exchanging natural Higgs, I can just replace the propagator by an I over m Higgs squared, and I can shrink down this interaction to a 4-point fermion interaction. So I can write an effective Lagrangian for this kind of interaction of the form chi bar chi times q bar q times 1 over m Higgs squared times some number. So because we expect these dark matter interactions to happen at low energies, instead of writing a theory with an explicit Higgs that's very heavy, instead I can just take the Higgs out of my theory. The technical term is integrated out, and replace the actual Higgs bouncing around by an effective operator that just connects chi bar chi with quarks. Because if I take this effective Lagrangian and I compute this amplitude, I would get the same answer as I would have gotten from my original theory, where my original theory interaction would be a chi bar chi Higgs plus q bar q Higgs. So the point is that this Lagrangian for low momentum transfer gives me the same interactions as this effective Lagrangian. And it's just easier to work with an effective Lagrangian than it is to work with the full thing with the Higgs, because I'm never actually going to see the Higgs in the process. So this is going to be our this is going to be what we're going to do. So I won't turn it up. So I'm just mentioning this as a motivation for the kinds of operators I'm going to write down. So I'm going to look at specifically operators that are called SS. The SS stands for scalar-scalar, as well as VV and AA. So the SS means scalar-scalar, and the form of these operators are going to have some coupling that I'm going to call DQ, and then a Q bar Q, and then a chi bar chi. So for example, this kind of scalar-scalar operator is a sort of interaction that could be mediated by integrating out of Higgs. And here, if we look at this DQ has to have mass dimension of -2, in the same way that the effective coupling up here would be some dimensionless number times 1 over mh squared. So you can think of this DQ as being something with dimensions of 1 over mass squared. For VV, we have some similar coupling BQ. And now, instead of having just nothing in between, I'm going to put a gamma mu. And finally, for AA, I'm going to write some coupling AQ, and I'm going to write Q bar gamma mu, gamma 5, Q, gamma mu, gamma 5, chi. So the reason for these names are that these combinations of fermions are both Lorentz scalars. So chi bar chi together transforms as a Lorentz scalar. So if I put two fermions together in this way, it transforms, or it doesn't transform under Lorentz, so it's a Lorentz scalar. But this combination, the chi bar gamma mu chi, or q bar gamma mu q, this combination transforms as a Lorentz vector. It has a mu index, and that mu index really is a Lorentz 4-vector index. And similarly, the gamma mu gamma 5, this transforms like an axial vector. So it transforms like a vector under Lorentz, but under parity, it picks up an extra sign. So question?
I mean, there are other possibilities like pseudo-scalar, scalar, or pseudo-vector.
Oh yeah, I'll get to that in a second. So I'm going to concentrate on these three cases. And it will turn out that these two cases will be similar, and they give rise to something called spin-independent scattering. This combination gives rise to something called spin-dependent. But of course, as Tibor asked, you might also be asking, why didn't I consider all the other possible combinations you could imagine? So for example, I could imagine having a vector combined with an axial vector, or I could have a scalar, or I could have a pseudoscalar. So a pseudoscalar would be something like q bar gamma 5q, where this is a Lorentz scalar, but it's odd under parity. And it turns out that you're free to consider those, but what ends up happening for things like essentially the other combinations, things like pseudoscalar, or let's say vector axial, or scalar pseudoscalar, or ... It turns out that for these other cases, when you compute the effective scattering cross-section, the effective scattering cross-section, you get your d sigma der for these ends up being proportional to powers of q squared. Or actually, sorry, I should say q squared over m chi squared. So put another way, these interactions give me cross sections that go like they're suppressed by powers of this, whereas the relative suppression of these is just an order 1 number. So these mixed combinations, you're free to compute them, but they end up giving more complicated combinations that are ultimately proportional to v squared. And these combinations, because v squared is like 10 to the minus 6, these combinations give you scattering cross-sections that are much, much smaller than these. So these are the cross-sections that people spend the most time looking for. More recently, people have been starting to think about these alternative cross-sections, but I'm going to concentrate on these canonical ones that give the biggest effective rates and that have therefore been looked at the most closely. Yes?
So a few years ago, there were like two data points, right? There hasn't been any more.
Oh, well, actually, there's a whole. I'll talk about that down the road. There's actually a big complicated story of some experiments actually have signals that seem to look like dark matter, but other experiments that would be sensitive to these signals don't see them. So there's actually a very confused experimental situation right now where some experiments, well, I guess there's one experiment that actually says it's found dark matter, and then there are other experiments that say that other experiments ruled out. So it's a bit of a mess, but I'll come to that after I've actually spoken about how to compute this stuff. What else? Okay, so I think I'll cap it there. So I remember I've made your homework due for tomorrow, but you might be able to talk Tibor into giving you an extension. But I will give you a new homework to start on tomorrow as well. You have a tutorial tomorrow, and but you're also free to come bug me. If you can track me down, if you have questions about the homework, feel free to ask me. What else? I'm in the office just a couple doors down from Tibor. And class tomorrow, no class on Friday. And I'll probably be just disappearing sometime after class tomorrow. So if you want to talk to me about the homework, today's better.